Afternoon. My name is Kiyoshi Morishita. I'm joined with group member Brendan O'Hanlon, and Jasper and Bryan are manning our booth right now. So our project is called Cryo Chamber, and we're rethinking the vaccine cold chain. So the problem is that vaccines are built on based on biological molecules, and as such, they need to be stored within a specific temperature range in order to function. And so there's a system in place to keep vaccines cold, and it's called the cold chain. So it's the entire infrastructure needed to ensure from manufacturing to administration, the vaccine is kept within this range. So why do vaccines break down? So how big of a problem is this? So this is a case study from Brazil. They looked at all the different reasons that they lost vaccines. So they saw that failures in the cold chain, and that includes power outages, where they lose power and the ability to cool vaccines, accounts for greater than 50%. And we're also targeting broken vials. So that's about 10% of the vaccines lost. So that's what we hope to address with Cryo Chamber. So what infrastructure is in place currently to keep vaccines cold? So the current solution is that they ship vaccines in styrofoam boxes with ice packs. They require specialized transportation, specialized cold storage rooms, and refrigerators with temperature monitors. And this is, it's quite expensive, especially when you consider developing countries where they don't have the infrastructure in place to support this. You see here that at more regional levels, the cold chain is more expensive than at centralized levels. So let's look at a case study. This is for Mozambique. It's a country in Africa. So first, the vaccines are manufactured in other countries. They then get shipped to the capital, Maputo, and onto the central vaccine store. So from there, they get distributed to provincial vaccine stores, and then onwards to district and more local health facilities. And there's a lot of elements to this chain, and the cold chain is only as strong as its weakest link, which means that if it fails anywhere, then the vaccine is lost. So what we're targeting with our Cryo Chamber device is the more regional levels, because at these levels, there's more variation in the cold chain infrastructure that they have. As well, the cold chain space is a lot more expensive at these levels. So that's why we're targeting the regional levels. So the primary objective of our project was to make a portable design. We want our device to be able to reach whatever local sites of administration, whatever the conditions in that place may be. We want to be able to store at least 50 vials at the 2 to 8 degree range. Furthermore, our secondary objective, we want to protect the vials from breaking. So during transportation and storage, if a vial were to fall, it could break. So we want to eliminate that possibility. And finally, we aim to alert the user if any of the vaccines have gotten out of range. And in that case, they would have to discard the vaccine.
All right, so how are we going to solve these problems? Well, we use the Cryo Chamber. Ta-da! So this is a device we built. You can open it up and show everybody. Currently, it holds 72 vaccines. It's not powered on right now, so it's at room temperature. So the device itself uses a thermoelectric cooler module. What this does is it takes electrical energy and it creates a heat pump. So there's a flux of heat from the inside of the device through the heatsink out into the ambient environment. This is powered by a lithium battery. So in the front of the device, we can't see it, but in there's the rechargeable battery. This one's a 20,000 milliamp hour battery. So if we run it at 1 amp, that means the device can last for 20 hours. Additionally, there's solar panels on the top to trickle charge the device when in sunlight. These can help improve the lifetime even further. The heatsink is on the back. This is a large heatsink, aluminum and copper. We could improve the thermal flux even further by adding a fan, This would take away from the power budget, about 100 milliamps, but could improve the power consumption of the thermoelectric device by lowering the temperature on its hot plate. The device features a microcontroller that can use a thermistor to measure the temperature inside. So it knows the temperature inside, and if it gets too cold, it'll shut the thermoelectric module off. If it gets too hot, it'll turn it back on. In fact, we're using pulse width modulation so that the device is always on, and it's changing the duty cycle of the pulses fed to the device to control the power that's dissipated across it. On the top, we have a LCD screen. It can tell the temperature to the user. You can see it here inside the device. It also shows the battery life. Additionally, you could push the button, and it could tell the user that the amount of time that the vials have been out of the temperature range, if that's happened. That way, nobody's getting administered a vaccine that's a dud. So nobody can get sick, nobody's going to die, because they know the vaccines are good. There's 2 vial holders inside. These are 3D printed to hold up to 72 vials, as I mentioned. The shell of the device is also a 3D printed module, but this is just a prototype. In the future, we would want to use injected molded plastic to fabricate the device. This is a somewhat simplified explanation of what's going on. So we've got the thermal domain and the electrical domain. The thermal domain, we have the cold interior of the device and the hot outside, so we can treat the ground as the hot and the voltage, the pulled up voltage, as cold. The thermoelectric module behaves as a current source, so it's pumping heat through itself, but it can also leak heat back through. So we model that with a resistor, and the same is true of the insulation. The thickness of the insulation will determine the thermal resistance of the box. So by increasing the insulation, we're decreasing the amount of heat that's getting in, and we can prolong the lifetime of the device. On the electrical domain, we have the thermoelectric module again, modeled as a resistor. We're pumping current through it, and we're controlling it with the FET there. The thermistor measures the temperature in the thermal domain and reports it back to the microcontroller to ensure that it's always in a safe temperature range. We ran simulations to better understand the system and figure out what's going on at steady state. It's not as simple as just saying we want 5 degrees on one side and 25 degrees on the other. It's acting as a heat pump, so the temperature on one side will affect the temperature on the other. So here we see we've taken room temperature vials and we've put it in a box that's pre-cooled, and we want to see how it behaves over time, and when it reaches a steady state that all the vials are cold. The vials inside the box are actually not in contact with the aluminum wall, so it does take some time for them to cool down. But the good news is that the vials should be coming from an already cold environment, so they'll be cold by the time they go in. In the next simulation, we took the cold vials and we shut the system off and we said, how long would it take for the vials to heat up? So here we see on the right that the aluminum box around the vials has warmed up, but the vials themselves have still stayed cold for at least 30 minutes. So even if the device, worst case, runs out of power, we can still keep the vials cold for an additional amount of time. If that were to happen, though, we would still display to the user that the vials have been out of range with a backup power. So I ran some tests. This was at home with just the insulation, the heatsink, the metal box, and the thermoelectric cooler. This didn't include the plastic and anything else. We started at 18 degrees, and we cooled down to 7 degrees, 8 degrees after 20 minutes. So our delta T is around 10, 11 degrees. This was running about 1 amp of current and about 4.5 volts, so roughly 4.5 watts of power. If we increase the battery voltage, we can further decrease the temperature. So when the temperature outside is warmer, say 25 degrees, we need that extra power to give us the greater delta T, the greater temperature difference across the device. And we also ran some drop tests. Our secondary objective to protect the vials, we put them inside the box and we dropped them from a height of 1 meter from all angles, so corners, edges, faces. The vials survived the drop each time, none were shattered. Then we took an individual vial, dropped it from a height of 1 meter, and it broke on the 3rd try. So we effectively shielded the vials from damage. So in conclusion, did we meet our goals? Well, yes, we demonstrated in one way or another that all of our goals are achieved. We regulated the vaccines down below 8 degrees when the external temperature was 18 degrees. So we could improve that by increasing the thickness of the insulation, increasing the battery size, having a larger heatsink, or adding a fan. We did the drop testing and they survived. We didn't test with the shell because we didn't want to break our prototype for the presentation, but this is something that we could do in the future. And alert the user that the vials have been out of range. That's currently not something that we've implemented in the software, but there's nothing limiting us from doing that. It's just a matter of time, somebody sitting down and coding, because the LCD screen works.
So stepping back and looking at the market, this graph shows the increase in capacity required in certain South African countries. For some of the countries, we see a dramatic spike in the amount of cold chain space required as a result of increasing populations and more widespread vaccination programs. So looking at the cost of this cold chain investment. So this graph compares the amount of cost required to store the vaccines, as well as the specialized equipment needed to maintain the cold temperature. And we see that the actual specialized equipment corresponds to a large portion of the cold chain cost. And this is the entire cold chain. We're only hoping to join in at the regional level. But as I mentioned before, this regional storage is a lot more expensive than the centralized storage. So we're hoping to account for a large portion of the orange bars here. For instance, in South Africa, this is about $50 million. So back to our case study in Mozambique. In Mozambique, they ship 75 million vials annually. And to maintain the cold chain in this system, it requires a capital investment of $28 million. The annual maintenance fee is $740,000. Now, how does CryoChamber fit into this? We're estimating, after mass production, a cost of our device of $200. I think that's reasonable because we're not going to be 3D printing our device in mass production. It'll be molded. So with this estimate of the cost, with a fully implemented CryoChamber in the cold chain, we can reduce the capital cost to $8.7 million. So a significant reduction in the capital cost. In terms of the annual maintenance, we figure that our device will be similarly as reliable as a fridge. It's a little bit difficult to estimate a long-term resistance of our prototype, but we figure it'll be on the same order. And if one of our devices breaks, it will be a lot easier to replace than replacing an entire fridge. So looking into the future, some things we can improve on. So the main thing is increasing the lifetime of our device. So that means improving the battery capacity, adding more batteries, for instance, or also improving the insulation. So if we have improved insulation, we will not need to have our device cooling for as long. We can have it resting in steady state at the desired temperature. Also, we would need to make sure our design is weatherproof. So currently it's not waterproof. That's one thing we need to do. And as well, make it resistant to dust and dirt. We expect the cost of our device to be lowered if we were to go to mass production. And a final thing, because we have these electrical components, it allows for the possibility of further improvements. For instance, if we add a GPS tracker into our device, we could track what vaccines are going to which locations and when. Oftentimes, this information is unknown. So from that data, we could then optimize the distribution schedules, ensure the right people are in the right place at the right time to make sure the cold chain runs more smoothly. As well, we could make a mobile app. And in this way, the user could get much more detailed information on the temperature history. So it's been out of range for this amount of time. It reached this temperature at this time. And have a better idea of the history of the vaccines. So we're helping the cold chain by reducing the capital cost. We're also reducing the cost of wasted vaccines, and we're providing a way to improve the cold chain. For instance, this data that we can get from this device is extremely valuable. So looking to other applications, This type of device could be applied to organ and blood transport, as well as the transport of other biological samples. Furthermore, it can be used for portable diagnostic devices, which require a certain temperature at which to operate. So we'd like to acknowledge all of you for being in attendance. We'd like to thank our advisor, Dr. Dongqing Li, as well as lab space provided by the SURF Lab. And finally, financial support from Waterloo Engineering. So we'd be happy to take any questions at this point.
So as a biologist, I have a question. Where is your novelty in this?
So there's no new technology, it's a new system. So the reason
So you took existing off-the-shelf components, like everything, all your circuits, everything is all just off the shelf.
So there are pushes to develop a system which is portable and can keep vaccines cold to go to remote locations. There's one common example people use. That's a project supported by Bill Gates. So this system is fairly large. It's about this size. It uses vacuum insulation as well as phase change materials to keep the vaccines cold for months at a time. So it performs very well, but the one issue that it has is it's not very portable. It requires at least 2 people to lift it and carry it around. So we went with the approach to make a device which was much more portable. So we can store 72 vaccines in this small device, and it can easily reach any remote location where the vaccine is needed.
Right, but how much does the Gates?
So his device, it holds 200 vaccines,
Okay.
and it costs around $1,000.
Okay.
So ours would be cheaper, and in terms of amount of vaccines stored for the amount of space that it takes up, ours would be better than his.
Right, but yours is only 1/5 the cost, right?
Exactly.
And it only lasts 20.
Yeah, so that's the one thing we would need to improve on is the lifetime of our device.
Okay. All right.
What's the current lifetime?
So
You say you don't know actually, but
running it at 1 amp current with a 20 amp hour battery means it'll last 20 hours. So right away, the easiest fix would just be to increase the size of the battery. The trade-off there is cost and weight. So we're making the device more heavy, and we're making a more expensive battery. But again, increasing the insulation, the thickness of the insulation, takes up more space, but it'll increase the insulation, the cold temperature inside, reducing the power consumption. So it's another trade-off.
so like this charging thing right on the top, and you get the sunlight charge, right? So how you calculate how much can that actually do? Right? So suppose if you use sunlight is hot, right? Then your system has to work harder. So does that actually can make the balance?
So the solar panels have an open circuit voltage of 5 volts and a short circuit current of 35 milliamps. So all 3 of them wired together in parallel, we expect them to give around 100 milliamps in full power or full sunlight. You could further increase that by plugging a larger solar panel in the front with a USB panel if you wanted to try completely running it off the sunlight, not using any battery power. That's something that remains to be tested.
So you did a simulation, right? So have you actually look at this, just the actual data in terms of the temperature stability over some time?
So we presented, I think, one graph earlier. That was a test from 18 degrees, a test for half an hour. Yeah, this one. So this was actual measurements, not just simulations. So we have the thermistor to measure the temperature inside the device.
What was the ambient temperature when you did that?
Yeah, so 18 degrees. My house is a bit cold, so we want to target 25 degrees or 30 degrees because out in Africa that's going to be the temperature out there.
What
And
about 40 degrees?
40 degrees would be a real challenge to keep. That's a delta T of 35 on the cold side.
I get that.
Yeah.
but in equatorial areas.
It's gonna use a lot more power, so you're gonna decrease the lifetime of the device. So again, trade-offs.
That was my question about the temperature. What is the limitation of your thermoelectric circuit?
Yeah, so we could do better than the delta T of 10 or 11 degrees that we have now by increasing the power that the battery's outputting. So the more power we put in, the the quicker the charge is going to drain. So what we'd want to do is the combination of increasing the thickness of the insulation, having a better heatsink or with a fan to lower the temperature on the hot side. We could also pick a better Peltier module that performs better for this application. These ones are,
They exist for various temperature intervals?
yeah, the ones that are on the market that we use are, for instance, for computers. You want to cool the processor on the computer, and that might not be optimized for this situation. Okay. Thanks, guys.
Thank you.